All right, good afternoon, guys. Let's get started on this first question now. Just jumping right off, as soon as you look at this question, they give you a balanced equation. And as soon as you see this balanced equation, at the very end, they give you something special. They give you a Kas are only associated with weak acids. That's the key. So as soon as you see this thing, you know that HF is weak. Now, hopefully you could recognize that HF is a weak acid. So we have a weak acid plus water yields the hydronium ion plus the fluoride ion. Okay? That's also how you can tell it's weak, because it has the water, hydronium, and equilibrium. Also, if it were a strong acid, what would this look like? If it were strong, you just write the ion, right? Okay, so that's another way you can tell. So that's just kind of looking at the very beginning. I really, really, really hope that you can do A without any hesitation at all. A is just write the equilibrium constant expression for the dissociation of HF. But here's the thing they do not tell you. When they say write the equilibrium constant expression, they're technically telling you to write K, right? But if you just write K equals and then write it, it's wrong. Why? Because for the dissociation of HF, which is a Ka, very good. It's just one of those things. You just got to be very explicit. And they try to do this to you. They try to just be very vague, yet want specific answers. And so they try to trip you up and hope you don't write the Ka. But it has to be the Ka. So really what we're writing is the expression for that. What is the only thing that will not be in this expression? Very good. The water, because it is liquid. Again, I'm just going to kind of write it up here. So, K, brackets, parentheses, what is it? Very good. It is brackets, all right? So we have H3O plus F minus plus all over F minus plus. Yeah, that's F minus all over HF. Okay, you good? Now, so far, you've earned 1 point. Yay. This is a 10-point question, so if you've earned 1 point, you've done something good so far. Don't miss the simple ones. Let's just be honest. If they make you write this expression, we all agree that that expression equals that number, correct? You're more than likely going to have to use this somehow. So keep that in the back of your mind. You're going to have to wiggle this thing around somehow to get something out of it eventually. Okay? And then here it is. Well, I'll tell you what, let me put this back up here so you can see. Then move on to question B. Guess what they just did? Calculate the molar concentration of H3O plus in a 0.4 molar HF solution. Already, guess what they asked you to do? They want you to move this thing around and calculate this part right here. Okay?
Teachers, this is an announcement, and A's ones who are...
All right, so here's the setup, essentially, is what we got to do. But what part are we solving for? H3O plus. You know what to do here, hopefully. We know we've got to get H3O plus by itself. Oh, that freaked me out. It was the mouse moving. But remember, what did we always set? And I'm just going to add this in. What do we always set Ka equal to? Remember, it was X squared over molarity. Remember what we did? And this is essentially what we have, because we know the concentration. So here's my suggestion. This is what I would do. I would do, let's see, H3O, after you've written this, of course, H3O plus equals Ka times, let me make sure I'm doing this right. Yeah, but it'd be Ka times 8, but you don't know this value. So times HF, and then I would do the square root of somehow, you see what I'm saying, manipulate it. Okay, let's start over. Let's start back over. All right, let's start back over. What we could do is, we know that it's going to at least be H3O plus equals Ka times, again, I'm kind of running through this a little, over F minus, right? All right. But the problem is we don't know what F minus is. So we always call that X. So it would be X, multiply both sides by X, which gets you the X squared. Bottom line is at the end, it's going to be X equals the square root of Ka times M. We've done this. You've seen this before. Okay. Where's your lack of connection?
Like, right, okay, what do you do after that step?
The blue?
Yeah.
Okay. We don't know F, right? So we essentially need it too. So what we would do is be times F minus and times F minus. So we have two variables of unknown, which if we substituted in as X, would be X squared. That's kind of where this is going. So it's just basically taking this formula we've always done and just plugging actual species into it. Yes, sir. I would have done this, and I would have went right to there. That's exactly what I would have done. I was trying to show it in terms of actual species of the reaction. But necessarily you don't have to have that. So then you have a Ka, you have a concentration, multiply them together, take the square root of it. All right? And so you get, tell you what would be really awesome is if I would be smart. Let's see, this is question 1 from 2007. Pop-up block. I don't want to. Okay, let's try this again. And then again, I'm gonna go through and work all these out for you, but I do at least want to show you what they're doing. Come on. You see what they did right here? You have and they plug in two x's because they're both unknown. And so they give you then blah, blah, blah. X squared is this, and you have to take the x squared. It's basically exactly what I did, but they actually show you the x part where you have to convert it to x squared. And what can we do with this 0.40 minus x? Y minus x. Why can we get rid of that? It's negligible, exactly. So essentially these values came from a rice table. That's where that came from. Okay? Ro, you with me at all? Don't worry about it. Yeah, that was just X. But that's how you get that. And I showed y'all that. It's back in your notes if you need it. Okay. So in the end, the answer to X, or the answer to the concentration, was 0.017. Okay, 0.017 once you solve for X. And that would be the concentration of the hydronium ion. Yes. Okay. What happened to the other one? There we go. All right, so that would be B. All right, then, notice what happens. HF reacts with NaOH. So let's talk about what happens real quick. HF, we know, is a what kind of acid? All right, we have weak acid. We know NaOH is a strong base. So who is going to win here? The base. All right, so according to this reaction below, we have HF. First of all, where did the Na go? Remember, strong is soluble. Group 1 goes away, so you only write the ion of strong. So we have the weak acid plus the strong base gives me a water, and then what would this thing technically be called? A salt, right? But why is it just the anion of the salt? Because technically, if we were to do the honors chemistry version, this is a double replacement reaction, right? What would your salt be? NaF. And what do we know about all group 1s? Soluble. Okay, so that's why it's F minus. Okay, a volume of 15 milliliters of a 0.4 molar NaOH solution is added to 25 milliliters of a 0.4 hydrofluoric acid solution. Assume that volumes are additive. What does that mean? They can change. That means you're going to have to add them together in this case. No, because you've already got all 4. You're not solving for 1. Okay? All right. So, but let me just talk about this for a second. If I have a really strong base and I add a weak acid to it, what's going to happen to the pH of that strong base? Is it going to go more neutral? So this is kind of like a neutralization reaction. All right. So this is exactly what's going on. This is just a neutralization reaction, okay? So part C, calculate the number of moles of HF remaining in the solution. And let's talk about that for a second. We know that NaOH is strong and HF is weak. So shouldn't strong win and suck up all of this HF? So why is HF going to be remaining? Why would HF be remaining if it's weaker? How much more of it? 10 more milliliters. Okay? So because of that, we need to know our mole comparison, if you will. So since we have 25 milliliters versus 15 milliliters, there is at least 10 milliliters extra of HF. Okay? So can all of the NaOH absorb all of the HF? No, because there's not as much of it. That is the key. Thank you. Okay? That is the key to that little aspect. So this is what we need to know. So the question was, how many moles of HF are remaining? So this is what I would write down. All right, so moles of HF equals moles of HF initially minus mole of NaOH added. Now, why am I subtracting those two things? It shows the difference, exactly. I started with a certain amount of moles. Where will I get that from? If you go back and look, they give you the volume and the concentration of the acid. How would you do that? What's the first problem? Change it to liters. That's the first key. How many liters is that? 0.025, right? Okay, yes, that's 0.025 liters. And I have the concentration. How do you get moles? This is one of those things that I'm begging you to know as a fact. We know molarity is moles per liter. How do you get moles? Liters times molarity. Okay, multiply your concentration times volume, and that will give you your number of moles. All right, so 0.025 times 0.4. So I'm just going to kind of plug this in as we go. So we have 0.025 liters times 0.4 molar gives me 0.01 moles of HF. All right. So again, the whole reason we're having to subtract is because this NaOH, right, it was strong and this was weak. So it dissolved as much of that HF as it could possibly dissolve. But again, we ran out of NaOH first, so it's kind of like the what? If it ran out first? It's kind of like the limiting reactant. Even though it's strong, there wasn't enough of it to keep taking this HF. So we got to figure out how many moles of NaOH were added. How could you do that? The exact same thing. They give you the volume and the concentration, except the first issue is they gave it to you in milliliters, so we don't want that. So we want 0.015 liters. Okay, exact same concept. So we have 0.015 liters times 0.4 molar. Okay, and that will end up giving you 0.0060 moles. Well, that should just then be an easy subtraction. What would it be? Basically, ignore the two front zeros. Very good. And that's how much is left. So it's real simple. You just kind of have to think through what's going on. Y is... All right, so let's talk about it. All right. This next part. Part D. Calculate the keyword here, molar concentration of F minus. Okay, everybody with me on that? The molar concentration of F minus. What do we know about molar concentration? What does that stand for? Molarity, which is moles per. All right. This is where that part up top comes into play. Assume that volumes are what? Additive. So that's got to play into some of your calculations. So what would be your total volume in liters? 15 plus 25 is 40. Okay. Now that's milliliters, so it's 0.04. All right, so let's come back over here. So we know we want the molarity of F minus. Okay. Well, we need moles, and we're going to talk about that next. But we know the volumes are additive, which is 0.015 liters plus 0.025 liters, which of course is 0.4. Now, I mentioned this a second ago, and here's where you're going to go wrong. If you get to this part, here's what's going to happen. Do you all agree that the last thing we looked at was 0.004 moles of HF? Here's the issue. You're going to take this number and you're going to want to plug it in right here. Exactly. But the problem with that is, I agree with you. Hold on, let me go back to this. We know that there was 0.04, that's actually 0.04 moles of HF, but what was the key thing? Remaining. Calculate the molar concentration of F minus where? In the solution. And the problem was, and I've already mentioned it, what do we call NaOH since it ran out first? That's the limiting reactant. So that's what you're going to have to use to convert. Again, this is the part that's real tricky. What was the concentration of the NaOH that we solved for? 0.06 molar. Yes? That was the concentration originally. Well, is it 2 zeros? Okay, I'm sorry. 0.006 molar. So we need to go from OH minus to what? So what's your mole to mole ratio? So it's the exact same. That's the hard part. The coefficients, mole to mole. Okay? So again, the hardest part is you recognizing that you got to come back to your limiting reactant. That's the hard part. So we know that this is our limiting reactant because it ran out first. And so then you go to your mole to mole ratio. All right, so essentially what we need to do is plug in 0.006 moles of F, and then you can do your calculation there, and I'm just going to give you the answer. It's 0.15 molar F minus. And this is why I picked this problem to do, because it started off in acids, it kind of got a little weird, and then the very last question jumped back into something that I hope you know. I hope you know how to do. Calculate the pH of the solution. Calculate the pH of the solution. So here's, let me double check, make sure I'm looking at this correct before I tell you wrong. Page of the solution. All right, we know. Okay, this is where it's going to get aggravating. All right. Yes, sir. And see, this is why I kind of get aggravated with this, because it goes back to the original. It goes back to the original equation, and I don't know how you would know to do that. It goes back to the original one. Let me just show you. I'll tell you what. Instead of trying to explain it, let me show you what they did. This is what they did. Calculate the pH of the solution. I've already given you the Ka, right? This is for the original one. You had to solve for the concentration of HF, which in part C we solved for the moles, and then we divided by the volume. Got the concentration, and then basically it was the... See, that's... I think this is a difficult problem because you would have never know where to get I'm going to be honest, I don't know how you would know to go back to the original equation because it never tells you that. Yeah, this is... Yeah, this is one of those that you've gotten to E, hope for about 4 or 5 points previous to this, and just kind of... It is. You can tell that it's not clear what they want you to do. Why do they go back to the original one? When I wish I had a better answer for this, but I do not. This is something that you don't know yet. I haven't taught you that yet. This is called the Haber-Bosch. Totally just went blank. It's the formula. It'll come to me in a minute. You don't know that one yet. It is, but what is the name? We'll get to it. All right. So again, that's kind of it for that one. So let's flip over and do the other. No, we're not going to finish that one. All right. Let's flip over. The other question was the same year, right? Nope. This is Form B. Yeah, same year, but Form B, and it was question 1 again. All right. All right, so let's kind of talk about the important things here to kind of look at. A sample of solid UO3. Now, first of all, I don't think I would really want to be messing with that. That's uranium. It's placed in a rigid 1.5 liter flask. If you have to do any concentration calculations, you think that's going to throw you off? Yeah, please don't miss that. Chlorine gas is added to the flask and is heated to 862 degrees Celsius. Now, first and foremost, I don't like Celsius. I'm going to change that. Somebody add 273 to that, please. 1,135 Kelvin. Okay, we may not even need it, but hey, let's go ahead and look at it that way. The equation for the reaction that takes place, and then notice, the equilibrium constant expression for the reactions are given below. Notice how they wrote their K. What form did they write it in? KP. Very important there. So since it's in KP, or even in KC, what is special about the correct representation of KP? It has the parentheses and the P. We had a long discussion about this in our meeting when I graded your mock exams. The only thing that you are required to write is the P. You technically don't have to have the parentheses. However, it looks better and more formal if you put them. So it was weird. If you had the parentheses but not the P, it was wrong. If you had the P but not the parentheses, it was right. So that is technically the only thing you're required to do. But I like having them both. It makes it look a lot more formal. Why was this thing left out, the U308? That's a solid. Very good. All right. When the system is at equilibrium, that is probably the biggest thing they could have ever told you right there. When the system is at equilibrium, the partial pressure of Cl2 is 0.17 atmospheres, and the partial pressure of this thing is that many atmospheres. Calculate the partial pressure of O2 at equilibrium. Okay? Calculate the partial pressures of O2 at equilibrium. Can I tell you how simple this really, really, really is? No, but why can't you plug in and rearrange? You agree that we have that one, and you agree, excuse me, that's the one we desire. We have this one and we have this one. We're looking for that. Why can you not plug in and rearrange? You don't have KP. That's the thing that you can't do. But remember, since we are at equilibrium, everything is, go ahead. I see your wheel spinning. Go ahead. Nope. It's a mole-to-mole relationship. That's all it is. And what's throwing you off here is the pressure part. If it was what is the concentration, you might say, oh, well, I can just do mole-to-mole. It's the pressure part that's going to throw you off. All it is a mole-to-mole ratio. So all you have to do is take this one, which is here, and go to O2, or take the chlorine and go there. But what do you notice about both of them? What is both of the mole-to-mole ratios? They're both 3-to-1. So it doesn't matter which one you pick. So it's just a mole-to-mole ratio. Now, to be honest with you, I'm probably going to put Cl2 because it's less to right. Hang on one second. But here's the deal. Somebody do me a favor. Do 1.007 divided by 3. 0.336. All right, let me just show you what they have, and let's talk about this one out loud, because there's something that I don't like here. AP Central, this is 2007B, sample response number 1. Let me just show you this, and there's a reason why I'm showing it to you. They set it up in the beginning as a rice table, and then I'll show you kind of what they did here. And I think I know why they did it this way. If it'll load. All right, to answer your question, why are you doing a mole-to-mole? Because the reason you can do a mole-to-mole is because everything is at equilibrium. So everything is comparable by ratios. There's not any going to change. This is what they did. Let's see if I can. So here's my question. They use this value, and they go to this one. Now, we all agree that it would be plus 3x plus x, and this would be minus x, right? Minus 3x, thank you. And why can we cross that one off? Because it's a solid. Why don't I do xx right there? It's going to be plus x. So essentially what you could do is you could just solve for x. You with me? Does that make sense? Let's do that. So this of course would be the exact same thing. So if you set those two things equal to each other, you'd agree you divide by 3? Why did it jump like that? My only thing is, and here's my thing, if you set these two things, 1.007 minus, or negative 3x minus that, it's not going to give you that value, correct? Are you with me? Bottom line is, this is what I want you to write. That's what I want you to write. Calculate the partial pressure. I may be looking at this too deep. Oh, I know why. Duh. Here's why you can't use this one. Because compare our I row. Compare your I row. That question mark has a value in here, right? So really, it's question mark minus 3x equals that number, right? Equals 1.007. I know if I said that long enough. So since we don't know this number, you can't solve for x. Exactly, because you're looking for two variables. That's exactly right. But over here, it's 0 minus 3x equals that big long number. So you can solve for x in that case. That's why it works that way. All right, I knew if I stared at it long enough, it would hit me. So that's why you have to use this one. Okay? That's why you have to use that one. So the way I would go about doing this, if they're asking for a product, compare it with the product. Does that make sense? They're asking about a product, so compare it with the product. Now, part B should be really, really simple. And I'm just going to kind of leave it like this so you can write the numbers down. Part B should be real simple. Calculate the KP value. Now what do? Plug your numbers in and solve. That's all you have to do is plug your numbers in and solve. Yeah. Yeah, I'll scroll back the other way. Yeah, because you have everything. They give you two of the values. You just solve for the third one, and it can work that way. Now, I want to be honest, that would be an absolute aggravation to put in the calculator. Be very careful here, and let me show you why. When you're putting this into the calculator, you've got to have e to the negative fourth cubed times e to the negative fourth. And then on the bottom, what else do you have to do? You got to cube it again, which makes it even. So that would be a tough calculation to mess something up on, or excuse me, an easy calculation to mess something up on. So be very careful when you're calculating this. Now, go ahead. Plugging in and going. Let me give you a word of advice. And this is a good word of advice because I've taught you this. And when we were grading your mock exams, we could tell the teachers who taught this step, and it helped. And here's what it is. Let's say if you get to part A and you have no clue how to get that number. And you're like, I'm skipping it. And then you get to part B and it says calculate KP. What should you do for A? Go back and make some kind of crap up where you get some kind of number and plug it into B and go. Because if you do some chicken scratch work, but say, all right, I'm going to say this is my answer, and it can be 1 billion. I don't care what it is, but make it logical. As long as you take that number and you plug it in, and your other calculation here works, you have to get that point. It's based off wrong answer. That's your BOA point. Exactly. And in this case, 1 point is earned for the correct substitution. For being a dummy and coming up with something intelligent looking and plugging it in, that's 1 point. And if your calculation works out, you get another one. So you get 2 points for making crap up and a step ahead of it. This is why it's good to know how to work their system and work their games. If you know without a shadow of a doubt. And the best part is, guess what? They gave you KP already, the expression. Now, if you can't calculate this, then you don't deserve the second point. But be able to make something up that sounds reasonable and logical and just plug it in and go.
Let's say we did do the first part, but we still made up a number.
You can't. They have to see where logic and reasoning, where that number came from. So let's just pretend that all of a sudden you did. Let's just say you picked this number and you said it was 1.007, and you did this ratio. And what was the number? You said 0.33 something? Yeah. 0.33, 6, I think is what it was. Again, this isn't right, but they can tell logically they knew you went from moles of this thing, or pressures of this thing, to pressures of this thing. You would not get this point because that number is not right. But if you took that number and plugged it in right there, which is where it belongs, you get the 1 point for the correct substitution. And if your math checks out, you get the second point. Okay. Yeah. Ignore the temperature. unless you notice that it changes. Because remember, the equilibrium constant stays constant at the same temperature. So if you go back and look up here, up at the question, let's go back to this. Got so many things going on here. Minimize here. Yeah. If you'll notice, and again, this is the view you're going to see. You're not going to see that other one, so it's a little bit easier to see. If you'll notice, the temperature they give you is right here, and then right here, and right here, and right here, and right here, and right here. What's all the temperatures? They're all the same. If you alter that value, it will alter what you have to do. So they have to tell you either at the same temperature or keep repeating it. Because remember, what is temperature dependent? Everything. So if that number changes, these values will be altered. You with me? Okay. Now, C, calculate Gibbs free energy change. Here's where you're going to freak. On the test, you're going to do this. They're going to say, write your KP, and then they're going to be like, what's delta G? You've got to remember there's a connection here. Negative rat link. You've got to remember that. If they all of a sudden just completely flip gears on you and they ask for something that you know is like K or delta G or E, look on the equation sheet. See if it'll jog your memory. And you will see that on this thing, let's see, it will be on the back under thermochemistry and electrochemistry. It says delta G equals negative rat link. Please don't mess this part up. Because somebody's going to do it if you have this equation. We know it's delta G equals negative RT ln K. Now let me ask you something. Let's say you butcher part A, you make something up, and you get a value for B, right? You know your B is going to be wrong. But however, if you get this equation and you know, but even though your K is wrong, will you still earn credit for C? Yeah. Yes. You just take whatever your K is and plug it in. But here's the part where I don't need you to mess up. What R is that? Let's talk about this. Gibbs free what? It's the energy R. And so if you're looking on your equation sheet, please rely on this thing. It gives you the things. It says gas constant R, and I really wish I could pull it up. I don't have a way. I don't think I could pull it up, or do I? Let me look. I know exactly where it is if I can just get to it in a reasonable amount of time. All right. AP Chem. Revamp material. Let's see. List. Perfect. There it is right there. I'm glad I have this to actually pull up and show you guys. It'll make a difference just looking at it. Yes, and that's what I was fixing to show you. That's why I'm pulling it up. There's a lot going on this computer, so it's wanting to run slow. And that's why I'm trying to teach you how to remember which one is which. I'm on. Let me go ahead and close that one. I know you're thinking. All right, so here it is. The first thing that I want you to notice is that right there. There's your connection, right? Your negative rat link to delta G. And so you go, okay, I know what Ln is. I just solved for K. Do you know a T value? Yeah. The key is, can you plug in that 826 they give you? Temperatures must always be in. Fantastic. So here's your R. We know that delta G is standard free energy. What is your unit for energy? Your unit for energy has to be joules. If you don't know what R to use, here is your gas constants R, and I hate the way they do this. Notice what they give you. They give you your numerical values, but then they also give you your unit, your units. Joules per mole, liters atmospheres per mole, or liters torr per mole. What do you want your answer in? So you should hopefully be able to recognize that J is in the unit. That's the one you're going to have to pick. Yeah, this is going to be in the front of your test. This is why I let y'all use it all the time. I want you to get used. Like, I hate to say this, but I really mean it. Rely on this thing. This is a cheat sheet. They give you a cheat sheet. Know how to use it. And so, again, your first connection is knowing how to pick that out. And then once you get the R, make sure you know that you're using the right R. If it's wanting delta G, we all know that's an energy. Make sure you use the joules R, which is your energy R. Okay? Now, so you should have the answers there to be able to just plug in. So I'm just going to show you this. There's your answer right there. Would it be okay if you left it like that? Say that again? Whatever, either one is fine. It does not matter. They like kilojoules because it makes it easier to look at. If it's ever above 1,000 or more, change it to kilo of whatever you're dealing with. Notice what just happened. If you are intelligent enough to just be able to maybe get through KP, and then you are really intelligent and you connect on this topic, even though this number may be wrong, as long as you plug it in and you use the right R, guess what? You get 1 point for writing it down. Don't mess those points up. Don't mess those points up. And I'm going to forewarn you. Number one, if you plug in the wrong R, it's wrong. You've done lost your 1 point for plug-in. You are allowed to plug in that, 1,132? Is that right? Yeah. 35, whatever the K value was, or Kelvin. You are allowed to plug that in. You don't have to show them that addition. You do not have to do that. Just plug in your K, your Kelvin, and move right on. And then make sure you plug in the K. Don't plug in some other number they've never seen. Don't put 1 in or anything like that. Okay? And then just make sure you do your calculations. So I personally believe you all should at least have 4 points at a minimum by this point. I'll give you a freebie on the first one. I would kind of see where you could miss that. But these bottom two, they are straightforward plug and chug problems. Okay? Now, I don't even know what's next, but I do want to ask you this. Based on C, spontaneous or non-spontaneous? Why non-spontaneous? It's positive. What would the sign of E be? Why? It's because it's the opposite of G. You see where I'm going with that? Okay, that's kind of what I want you to kind of get in your head. What would K be based on its number? I should have actually already asked you that. Remember, we have the geek factor. Okay, for spontaneous reactions, what do we like G to be for spontaneous? Gangsters are? Voltage is good, and K likes to be greater than 1. So far we have determined K is what? Less than 1, which makes it non-spontaneous, which then automatically makes all these other things flip. Yes, sir?
So when you said that delta G would be such and such based on...
That's exactly how you have to do it.
So you don't have to show that?
On what part? Is D, what is it?
It's asking for delta S.
State whether delta S for the... No. Delta S is totally different. What is delta S?
That's,
Delta S is what? What does entropy mean? Disorder. So let's talk about it. It's going from a solid and a solid and 3 moles of a gas to 3 plus 1 mole to 4 moles of gas. What's happening? More disorganized. Now, this is the tricky one. What does nature prefer? So it's going to be fantastic. It's going to be positive. So here's their explanation of why. Delta, and I'm leaving it short because I don't want to show up anything else. Delta S is positive because 4 moles of gaseous product are produced from 3 moles of gaseous product. Here's what I would say. I would say you're taking a solid and you're converting it into 4 moles of gas. Talk about the solid. If you ever have solids or liquids, use those. But their example is fine as well. All right. Let's go to math class for just a second. No, it's really simple. Matter of fact, let's go to geometry. It's even better. This is an XY coordinate plane. What would the sign of the x-axis be? And let's see, what's our quadrants? Is it 1, 2? Whoa. 1? Where? Top left? 2? 3? Okay. All right, so in quadrant 1, thank you. I thought it was... Yeah. Very good. They're both positive here. So positive, positive. Negative, positive. Negative, negative. All right. Now, we can use this for thermo as well. Give me just 1 second. I'll probably have to do it at the end, but I'll show it to you. We want entropy to be what value? All right, so we want delta S, which is entropy. We want it to be...
Wait, is this still D?
No, I'm going on to E now. I'm talking to teach you how to remember some of this. What do we want S to be?
We want it to be negative.
Try again.
Positive.
What is delta S? Entropy, we like disorder, right? What is delta H? What is it, first of all? Enthalpy tells us our thermicity. Exo or endo. What is thermodynamically favorable?
Negative.
Which is negative, right? This is what we desire. This tells us true thermodynamically favorable. So which coordinate... See, I don't remember... Yeah, it's the coordinate... And I always forget which one is which.
Wait, what are you talking about?
I think this is delta H and this is delta S. Let's just go there. Okay, let's go there. So which one of these, delta S is Y, delta H is X, which one of these will give us true thermodynamic favorability? 2. Everybody agree with that? So this is thermodynamically favorable always. You agree? You with me? GP at all?
Yeah.
Okay. JC, you good? No, let's look at it. These are the two things we desire. Delta S is your y-axis. We want it to be positive. Delta S is positive up here. Delta H we want to be negative. It's the x-axis. Well, these are the only two locations where we have both things fitting. Okay. Let's go to quadrant 4. Now delta S has become what? Negative, and delta H has become. That is the complete opposite of what we desire. So what does that mean in terms of thermodynamically favorable? Never. Never TF. All right. That quadrant, when it's a positive delta, when it's a negative delta S and a positive delta H, because it's opposite, both of them are opposite. Now we have the likes. Okay. When they're both positive, they are both TF, thermodynamically favorable. But when they're both positive, does anybody remember? Only at, very good, at high temps. The way you can remember that, 2 double positives makes you a really high temperature. So what does that make the 2 negatives? Only at low temps. So look at the temperature that they give you on that question. Would that be really high or really low? That's crazy high. What is boiling in Celsius? 100. Look at the Celsius temperature. 826. That's pretty high. Is it 862? Okay. That's even higher. So the fact is, this is only going to be dealing with something up here. Bottom line. Okay. Now, again, this is just a little tool to help you kind of remember true things. So state whether, again, let me get out of this view. I don't want you guys to see the key view. I want you to see this view. State whether the enthalpy change for delta H is positive, negative, or 0. Justify your answer. So far, we know that K is less than 1. We know that delta G is what?
No, sorry, positive.
It was positive. And we know that delta S was what? Positive. Everybody okay with that? So based on these two things, we know that it's non-spontaneous, correct? However, this one's positive. So if we go back to this thing, what do you think it's going to be? Huh? Only at high temperatures. Okay. So state whether the enthalpy change of delta H is 826 is positive, negative, or 0. I'm going to, and let's go back and let's look at the key, just to double check, make sure. I don't want to sound like an idiot. Both delta G and delta S are positive. True. Thus, H must be positive because delta H is the sum of the two positive terms in the equation. Ghetto homies take speed. That's ghetto homies take speed. Okay. So since G and S are both positive, that also makes H positive. No, I could teach it off of that. No. I understand. But here's the deal. Okay, well, fine. I won't. Where? Never. Never. Yeah, absolutely. Now, here's where you're going to mess up. And I'm forewarning you, some of you would miss this. At a certain period of time, 1 mole of O2 is added. So as soon as they tell you something's added, you're probably going to be doing a little bit of shifting, right? So 1 mole of O2 is what? So we're adding here, correct? F. After a certain period of time, 1 mole of O2 is added. All right. So according to Le Chatelier, we shift how from an addition? So what way are we going to go? To the reactants. So what's going to happen to the concentration of your products? The concentration should decrease over here. And what should happen to the concentration of your reactants? It should increase. And here is where you're going to miss it. Does the mass of U3O8 in the flask increase, decrease, or remain the same? Here's what you're going to say. It's going to remain the same because solids do not affect equilibrium expressions. Or do not affect the equilibrium. That's what you're going to want to say. This is wrong. Here's what you're going to want to say. Because it says, does the mass of U3O8 increase, decrease, or remain the same? You're going to want to say, it stays the same because solids, right, don't affect equilibrium. Here's the issue. Am I adding or removing some solid from this? What am I adding or removing? I'm technically adding O2. So since I'm shifting, will it still affect the solid? Yes, because here's what's going to happen. What's going to happen to this when I shift back towards the reactants? We need that thing to go down, right? So these things are going to come together and they're going to remake some of your products or your reactants. So your chlorine will also go up, and what's going to happen to your solid? It's also going to go up as well. So it will increase. The only time you would say it doesn't affect it is when you are adding or removing the solid itself. Solids can be affected if you add other things. So again, let me just show you their key to kind of justify what we've been talking about. The mass of U3O8 will increase because the reaction is equilibrium and the addition of the product creates a stress. And again, you don't have to talk about that. You can just say that we're adding to the product side. The reaction proceeds from right to left, or it shifts towards the reactants to reestablish equilibrium so that some O2 is consumed, blah, 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 blah. And that is produced. So you could really shorten this up and make it a lot less wordy, but a lot more, and still create the same accuracy.
If you do reactions at equilibrium,
increasing the product, increasing the concentration of the reactants. Yeah, increasing the concentration of the reactants. Yeah. All right, so that is that one. Now, so that is the end of this recording.